Can we turn off the house lights here so you better see the pictures, please? Okay, the LROC Lunar Reconnaissance Orbiter camera is actually 3 cameras. It's 2 narrow-angle cameras, or monochrome, that have a resolution of about 50 centimeters per pixel. That changes a little bit as the orbit evolves. And then the wide-angle camera, which tends to not get as much attention, is a 7-band multispectral imager that sees down into the UV down to 320 nanometers and out to 689 nanometers, and it can image the whole moon every month. Okay, just to give you a little update on the amount of data that we've got on the ground and how much opportunity there is for you to do your research. We get about 400 gigabits of data every day. There's 371,000 NAC images on the ground right now. 328,000 of those are of the illuminated surfaces of the moon. As you can see, we take a lot of images that are calibration. They're very small. So that number is, that 371,000 is a little inflated. So this is really the number. There's about 60,000 images with an incidence angle less than 45 degrees, which are incredibly valuable for looking at morphology, and turned out to be totally fascinating, at least to me. And that translates into 6 times 10 to the 13 reflectance measurements of the surface of the moon. It's a lot of data. There are about 160,000 WAC images on the ground, about 90,000 of them in color, which cover the moon approximately 20 times. And then there's about 17,000 black and white images, and those are mostly of the poles. We take an image of each pole about every 2 hours to map out illumination conditions at both poles. I think we have covered about 20% of the moon with the NACs right now, and it's my goal over an extended mission to map the whole moon at resolutions ranging from 50 centimeters to 200 centimeters per pixel. And that will really be LROC's legacy for the lunar science and exploration communities for the next 100 years. I'm really looking forward to that. Whenever we have reviews and so on and so forth, especially right after launch, we have to show an MTF diagram which shows how well your instrument is in focus, which is a big question for the narrow-angle cameras because they were designed such that they were out of focus when they were on the Earth, and then when they get into the space environment, they slowly go into focus. So you can imagine that made me quite nervous. But I think this is much better than an MTF diagram. This is the descent stage of Apollo 11 sitting on the surface, and you can actually resolve the foot pads and the seismometer and the other pieces of equipment that were left on the surface in a high sun angle image. So this just shows you that the camera is performing well, way better than I had hoped. Okay, one of our major goals at the beginning of the mission was to image these constellation regions of interest, and this just shows you the locations across the surface. And these are areas of potential spots for future exploration. They're landing sites, even though they're called something else. And we did a fantastic job of imaging all those. I'll show you 2 very quickly. On the upper left is a WAC-based mosaic. The little 3 nested boxes shows the strategy that was developed by ESMD, 10 kilometer, 20 kilometer, and 40 kilometer box, and we had different goals within each box. Down here on the left shows the same box overlaid on Lola base map, which gives you really great synoptic topography. Then over here to the right, you can see as we've been reducing these data, the stereo narrow-angle camera images that are on the ground, how we filled in the 10, the 20, and much of the 40 kilometer box. I know I just targeted another stereo pair yesterday before I came out here, so we will eventually fill this whole area up. This is of the Hortensius domes, which are some fascinating low relief shield volcanoes in Mare. Okay, this is a picture of the Lichtenberg crater digital terrain model made from narrow-angle camera data. This is a regional view showing the WAC digital terrain model in the background. Here you can see the reason this is a constellation region of interest is this is one of the youngest Mare basalts on the moon, and we do not yet have a sample of a young Mare basalt. So this major question of when did Mare basalt shut off is still unanswered. So this would be a really great place to go either with a simple lander to retrieve a sample from down in here, or a rover to explore the area, because you could easily access 2 different MARI units plus Lichtenberg crater itself, which is about 20 kilometers in diameter. And this just shows you to help you get you excited about the quality of the data, as we're now getting time to reduce it into data products that the science community can use. And there are NAC digital elevation models that are on the LROC webpage, and we will continue to post them over time as they're completed. One of the fascinating discoveries early on with the NAC data, was that there are these low-bait scarps that were known to exist in the equatorial regions of the moon discovered during polar eras, but now they're all over the moon. And these little white dots show where we have discovered them. There's now, I believe, 75, at least that's what it says on the slide here. I think that's actually more than that, because as we image more of the moon, we discover more and more of these. And these scarps, the fact that we now know that they're globally distributed and have random orientations, definitely fits the story that the moon has been shrinking over time, and it is still shrinking due to the change in the state of the core from liquid to a solid. And the reason that we know that these are young is that they have, in many cases, very few to no impact craters on them. And they also are very small scale features, maybe a few to 10 meters in relief, and they bulldoze over and destroy very small impact craters which have a limited lifetime on the surface of the moon. So they're probably, some of these are tens of millions of years old. And another great result is that this whole idea of the shrinking moon, gives you the very simple stress regime picture, but it's not as simple as we thought, because in some areas we're actually seeing regions of extension in the far side highlands, which are not all that easy to reconcile with current theories of what's going on the moon. Okay, another discovery is that the Compton-Belkovich region, which was known from lunar prospector data to be a thorium anomaly and from Clementine data to be an albedo anomaly, by examining the black color, which shows it to be a red spot, and the NAC close-up photography, and the digital terrain models that we produced, and combining with the results from the Diviner instrument, which shows it to be high silica. Now we know that this is a region of high silicic volcanism on the far side of the moon. What is it doing there? It's not around any other volcanic features by a long shot. It's very amazing. This result is coming out in a paper by Jolliffe et al., which probably be out in the next month. Not sure what that's doing up there, but maybe I did that by pushing the wrong button. What it's covering up is the little title that says MARI pit craters, and we see these, they were first discovered by the Kaigui mission, and we did follow-up photography at 20 times higher resolution so that you can see down inside the pits. And here's fantastic pictures of the floor. But when I first saw this, the thought was, well, I wonder if this really is an open lava tube, and is there any way that we can look underneath by tilting the spacecraft over and see if there is an open void or sublunarian tunnels. And lo and behold, the very first image that we took, we were able to image underneath the overhang. See those 3 boulders right there? Those are those 3 boulders right there. So what you're seeing right here is underground on the moon. So this is a fantastic discovery. So what is the significance? Is it just something that's way cool? Well, yeah, it sure is. But when we went over to the other pit at Marius Hills, we did the same thing and saw a sublunarian void again in the Marius Hills regions. But these are very important because they're ready-made shelters for future lunar explorers. And one of the things that we can see in these off-nadir images is that there's very thin layering in the walls of these pits. So you've got a beautiful geologic cross-section straight through. And this has important implications for understanding Mari basalt emplacement because it shows that they're placed in very thin flows, a few meters to 10 meters thick. So one criticism is this, well, maybe the pits form in these weird areas where there are only thin lava flows. I'll address that in a minute, but I don't think that's true. But if you could get down inside these tubes, you might see perfectly preserved flow features because they've been protected from micrometeorite bombardment, possibly sublimate minerals. And there's a fascinating possibility that maybe exposed in the walls of these, you can find old regolith layers between Mare basalt flows that might have a record of the solar wind in them. We don't know how extensive these are right now. Maybe you can only go back 20 meters. That's about how far we've seen, but maybe you can go back 100 meters. Maybe you can go back a kilometer. I'd sure like to find out. 2 minutes? All right, well, that's not what that clock up there says. Okay. All right, well, this shows that, and you look at impact craters, that there's, that these thin layers are very common when you see in Mare basalt, craters in the Mare basalt. And also another fascinating discovery is we're finding similar features in impact melts. So this shows that impact melts have an advanced plumbing system in them also, so they're very complicated structures. Okay, the WAC, which I mentioned earlier, doesn't really get as much attention as it deserves. Here's a picture of it. As you can see right here, as it was being put on the spacecraft, it fits in the palm of your hand, and yet it images the whole moon every month. And those are not redundant data. This is just a quick preview of the one of the global color mosaics. We've also reduced all of this redundant coverage into a topographic map at 100 meters per pixel. And this is done by DLR, and Frank Schulten is leading up that effort. And here's just a short list of highlights, science highlights, and exploration highlights. And I won't go through all of this because I want to jump to a movie here. But just let me point out in the background right here, you're looking at a 9,000-foot scarp. 9,000 feet. This is the wall of Giordano Bruno crater. This is a oblique image that we took about 2 weeks ago. It's one of the youngest large impact craters on the moon. It's thought to only be something like 10 million years of age. It's very spectacular. Okay, this is just highlighting the global nature of the LROC WAC data set, and it's a fantastic monochrome base map for doing morphology and stratigraphy. It's also been reduced into this global topography at 100 meters per pixel. This map is at the poles. We only go from minus 80 south to plus 80 because of all the shadowing. So we filled in the polar regions with the beautiful LOLA altimetric data set. So what you're seeing right at the poles is LOLA, but everywhere from 80 south to 80 north is the wide-angle camera stereo data set. It'll be over in just a second. Okay, well, there we are. There's a huge amount of data out there, and I invite everybody to dive into it. The LROC and the LRO mission itself has been incredibly successful, and there's lots of work to be done.
Any questions for Mark? Bring the house.
Have you seen any degradation in the cameras at all during the mission?
Any degradation in
Yeah, is there any degradation in the quality of the images?
I wish you wouldn't ask questions like that, but no, it's not good. It's not that I'm superstitious.
Let me just follow up then, so it can go for a long time.
Yeah, I think we transitioned to the fixed orbit something like December 11th or December 12th, which is a low energy orbit, which has a periapse of about 30 kilometers over the South Pole and an apoapse of 200 kilometers over the North Pole. So our resolution will range from 50 centimeters to 200 centimeters, but it's a low energy orbit, so I suspect when we do that transition, we'll have something like, well, that's not wood, is it? But 5 or 6 or 7 years of fuel on board the spacecraft. So that's when you would start worrying more about reaction wheels or solar array gimbals or the antenna, something like that. Moving parts failing. But again, like I said earlier, a real important legacy to the future of lunar exploration is mapping the whole moon with narrow-angle cameras and collecting as much of that stereo data as we possibly can to make these And the topographic maps that we're making are higher resolution than when you go to REI and buy a topo map to go on a hike, in the mountains around here. Now imagine having that resource if you're planning a rover traverse or a human traverse somewhere on the moon.
What are you doing to facilitate, enable public access to this 400 gigabytes a day of imaging data?
Well, that's a great question. I don't know where it's coming from. It's like the voice from, oh, right there, okay. I guess you haven't been to our webpage. We have 4 different interfaces depending on the type of user you are. When someone's just a casual browser and they want to have a Google Earth type experience where you start out with the WAC data and you drill all the way down and you just keep zooming down to 50 centimeters per pixel with narrow angle cameras, to a more sophisticated where you've got, like I use it a lot, a little nerdy thing where you type in your lat long range and your incidence and emission sorts, and then you get the data that way. And then there's an intermediate, a WMS map server. It's kind of intermediate between those two type of interfaces. So it's really easy to get to the LROC data. And we've also put all of our processing software, the camera models and the calibration, into a software called ISIS. It's distributed by the United States Geologic Survey. And it was one of my major goals is to make the software to process this data, completely accessible to both science community, but in general public. Anybody can download this data set. And we also put reduced data products out there, global map of the moons out there from the wide angle camera. Many of these DEMs that you've seen here are out there, and other reduced data products. And we've actually delivered much more in terms of reduced data products and interfaces than NASA originally had envisioned and paid us to do, because we love what we do so much we can't stop working. Oh, yeah, and we have featured image 2 or 3 times a week, which Lillian just shouted out because she puts a lot of time into that too, which is really a lot of fun. And if you go look today, there will be new one out this morning. In fact, well, what time? Now it'll be out in an hour.
Bill?
So what are the plans for this mission after the first extended mission? Does NASA have plans to continue this on until it runs out?
Well, no, they don't. And we're writing a proposal right now to compete with other missions that are in extended phases. I think there's six missions that will be competing for those type of funds. There's 3 or 4 Mars missions, Cassini, so on and so forth. So it's our job to make a really bulletproof proposal that NASA can't not fund. And I think that should be fairly easily. I mean, once you get done with this conference, you're going to see that the moon is a very beautiful and mysterious place that we really don't know a lot about, but now we have the data to start answering the questions. So frankly, I'm not too worried about us making a really strong case to continue for, I think it's a 2-year mission, and then when that's over, we would have to compete again for another extended mission.
Right, thank you.